this is a sort of a general direction that most of you know I've been kind of obsessed with for, I don't know, 8+ years at this point. And this really is some kind of departure from everything that we've known how to do. It's something that's been something I've really wanted to do since the very beginning. And so this is a kind of a distinct bit of progress over the last year. So this is joint work with Chenghao, who's probably asleep, maybe here though, I don't know. But yeah, he'll show up. He's been here every day. So, you know, find him, bug him with questions or whatever. And Yury, Polyanskiy, who you all know and love. All right, so good. So as Ankur said, this is about some sort of variant on Planted Clique. Okay, and I'll tell you more about that. But really, the focus is not necessarily really on Planted Clique, and really more on this dependent. Okay, and so we're going to try to understand general average case reduction techniques to address dependence in probability distributions. And we're going to focus on a specific case. All right, so our setting is, well, we're going to start with something close to Planted Clique. It's Planted Dense Subgraph. There's two hypotheses. You're supposed to decide between the two of these, given observation of a graph. So you either observe an Erdos-Renyi or you observe an Erdos-Renyi where a smaller Erdos-Renyi of higher density, so GKQ, has been planted inside of a GNP. So P is the ambient edge density, Q is the sort of elevated edge density. If P and Q are constant, so you could think of P as half and Q as 3/4, this behaves essentially identically to Planted Clique. And among other things, the conjectured hardness and sort of phase transition to easy is the same as Planted Clique. Okay, so conjectured to be hard for K, the size of the clique that you're, or the size of the dense subgraph that you're planting, less than or down, and it's easy above that, meaning there's a Polyanskiy time algorithm. Okay, so for the purposes of this talk, actually this doesn't matter at all, not even a little bit. We're completely agnostic to whether the threshold of Planted Clique is actually at root n or at end of the 1/3 or whatever. So there's been a ton of work, by the way, really focusing on Planted Clique. And for us, the conceptual focus is less about specifically where the threshold is for Planted Clique, but more about understanding, can we translate what we know from a problem like this to other problems? So sort of a universality question. All right, so with that in mind, there have been a lot of results that start with this particular phase transition for Planted Clique and conclude other sort of phase diagrams or hardness regions for various other problems. Just as two examples, there's Gaussian biclustering of Yihong and Songming. Yihong maybe is here, maybe he's again asleep. Yep, back there. So you know, he's one of the original people who were doing reductions from Planted Clique, two statistics problems, and concluded this nice phase diagram where there's this hard region. That hard region is hard, assuming that the region in Planted Clique is hard for less than root n. Here's another problem, spiked Wigner. There's a somewhat different phase diagram. This is from a paper of mine with Matt Brennan and with Chenghao from a few years ago. And the point is that this shows the sort of reduction from Planted Clique to other problems or between other problems shows fundamental relationships between the problems themselves beyond just these hardness diagrams. And motivated by that, this is a sort of diagram of reductions, web of reductions, almost entirely from this paper with my former student, Matt Brennan. We start with not exactly Planted Clique, but something very close to it and map to this wide variety of statistics problems. You can probably find a problem that you care deeply about or have thought about. There's some version of a stochastic walk model here. There's various other, there's robust estimation problems, robust partial linear regression, et cetera, various other problems. Okay, so this is from 2020, and you know, this is in some level satisfying because it explains what's happening. So we can think of this kind of more broadly. What's the philosophy of sort of complexity theory at large? And specifically for statistics problems, well, we have many complex statistics problems, right? There's gazillions of problems here, and there's many others that aren't in this diagram. And the point is that on some level, at least understand something about these problems, one can instead focus on this very simple problem, Planted Clique or Planted Dense Subgraph, right? That's the philosophy on some level of complexity theory. Now, one thing to emphasize is that these sorts of reductions, this whole approach is algorithm independent. So these are relationships between problems that hold for any algorithm. Somebody might come up with a new algorithm next week, and it doesn't matter. The fact that this problem is connected to this other problem holds completely independently of which algorithm you're thinking about. You know, that's not to say that studying restricted classes of algorithms isn't useful. It gives a sort of complementary perspective. For one, it really raises the stakes in understanding a problem like Planted Clique. And second of all, one can get certain insights from studying restricted classes of algorithms even for these statistics problems. So these approaches are very much complementary. Okay, now the big thing that probably some of you are wondering, okay, there's this web of reductions. It's actually all one way. It's a directed tree. It's kind of going outwards. And so this is only a partial order of relationships between problems. Why might we hope for more? Well, we have, since the beginning of complexity theory, the NP completeness, which tells us that there's a whole lot of problems that if you could solve them, then you could solve 3-sat or k-sat, k bigger than 3. And not only that, but it goes both ways. And this both ways statement is profound because it says that all of these are completely equivalent in their complexity. And so you really can, on some level, just focus on 3-sat if you want to understand these problems. And there's thousands of them at this point. So it really is a big simplification in kind of the conceptual landscape. And so one might want to do the same thing with the various planted statistical problems that many of us study. And so far, we don't have any of these arrows going back. Okay. So what's missing? What do we need in order to do that sort of equivalent statement in a non-trivial way? Well, here's a motivating example. So here's sparse spiked Wigner. We have a rank 1. I'm supposed to not point at the thing because I'm obscuring. We learned that yesterday. Okay, but I have this really cool pointer. Yeah. See, okay. Even better than my arm. Right. Actually, it has another mode. Let's see. There we go. I can zoom in like crazy. Okay.
Yury, are you taking notes?
Yury, I can share this. You know where to find me. Yeah. Yeah. So, all right. So there's a rank 1 spike there, and it's sparse. This U vector is sparse, and you're adding a Wigner matrix. So basically, just think of it as just independent Gaussian noise. It doesn't matter if it's symmetric or not, as far as this problem is concerned. And so the point is that you just have this rank 1 thing. This is kind of the cartoon of this. You have this rank 1. U transpose plus independent noise. Now, another problem that's very well studied, including by people here, is sparse PCA, in particular under the spike covariance model. So here, one observes independent data that's from some multivariate Gaussian, where the signal now lives in the covariance matrix. So there's this sort of very similar looking rank 1 spike in the covariance matrix. And if one forms the empirical covariance matrix, sigma hat, subtracts off the identity because that's sort of not so meaningful. And looks at it, the cartoon is identical to the one before, except for we have a Wishart matrix instead of a Wigner, and so the entries here are dependent. So you can think in particular that these 3 entries are dependent. And so then the question becomes, well, I should say, we know how to do reductions from like Wigner to sparse PCA in a very strong sense, but what we don't know how to do is the way back. Okay, so clearly what we need to do is understand how to remove dependence in the noise distribution. All right. Okay, so the goal in this talk is to show non-trivial reduction that removes dependence. We're going to actually end up with strong equivalence between problems. And of course, the eye here is towards developing general techniques that are broadly applicable and advance our way of doing this whole business. Okay, so one thing that should be obvious by now is I'm actually going to try to go, essentially, I'm going to err on the side of going too fast. And so that's because there's some ideas that I want to get to at the end and actually be able to dwell on them. For many folks, this initial bit's going to be kind of boilerplate, but if there's something confusing, especially notationally or whatever, just interrupt. Just yell at me. So questions are welcome.
Yes.
Planted Dense Subgraph. So perfect. Yeah. Okay, and again, for us, PDS, I'll emphasize, but it's for constant edge densities, 1/2 and 3/4, whatever. All right, so first things first, what's a reduction? Okay, well, there's actually multiple ways of defining a reduction. We're going to use the particular definition. So we're going to say that problem P reduces to problem Q. And again, this is hypothesis testing problems. Everything here generalizes to estimation problems, but much easier to just write down things for hypothesis testing problems. Okay, so we have P0, P1. Yeah, P0, P1, right? The 2 hypotheses, the 2 probability distributions. And we're going to reduce to Q. We're going to say that there exists a reduction to Q if there's an efficient polynomial time computable randomized algorithm satisfying that it maps each of the 2 hypotheses to the correct Q distribution. So P0 gets mapped to Q0, P1 gets mapped to Q1. Now, this little sub epsilon there, that is measured in total variation. So we don't precisely map P0 to Q0 and so forth for P1. We actually get something that's close in total variation. You don't have to measure it like this, but this is convenient for statistical problems because the errors basically translate in a nice way. And then the obvious remark is that this does constitute a reduction. In particular, if you have an efficient algorithm for Q, then you can immediately get an efficient algorithm for P just by converting problem P into problem Q using the reduction. And then whoever claims to solve problem Q is now solved problem P, right? Okay. We're going to work with particular dependent distribution. We call it the random graph with triangles for reasons that will become evident in a moment. So we start with an Erdos-Renyi, GNP. For every triple of vertices, we add, so we take the union with the triangle with probability P prime. Okay, so independently, for every triple of vertices, we just add a triangle. This is done for all of the n choose 3 triangles. Turns out that kind of the interesting regime, or at least the regime that we can handle, is P prime is on the order of 1 over n. We'll actually take 1 over n log n. And the reason that 1 over n is kind of meaningful regime or meaningful threshold, you might not want to take P prime too much bigger, is that any particular edge here, you can ask what's the density after you've added all these triangles. Each edge is present in order n triangles. And so the shift here in the mean is constant, right? So if you're adding more triangles than this, pretty soon you're going to just end up with a complete graph. So this model obviously has some low order dependence. If I tell you that there's this edge and there's this edge, then the third edge is more likely to exist than otherwise. So this is exactly kind of capturing the phenomenon that we care about. You might ask why triangles? Well, you could add 2 stars and that's fine too. Triangles somehow look nice. You can draw nice pictures and so forth. But you could certainly consider 2 stars. You could consider other small subgraphs. You could add 4 cliques if you want. And so this will sort of generalize in obvious ways that are obvious maybe to some subset of the audience. All right, so the first question before one does anything, one might ask, how many triangles do I need to add to actually get something different than Erdos-Renyi? Turns out that one can calculate this threshold. So if P prime is bigger than this n to the minus 3 halves, then one arrives at something that is substantially different from the starting point. This no longer looks like Erdos-Renyi, the TV is close to 1. If, on the other hand, P prime is below this threshold, then the TV with Erdos-Renyi is going to 0. So it's sort of one hasn't done much by adding these triangles. And of course, the heuristic here is just comparing the number of triangles with the standard deviation of the number of triangles that existed to begin with. Okay, so the main point here is that we're operating well above this n to the minus 3 halves. We're adding enough triangles that this is very, very, very different from the starting point. Another remark, so some of you might see triangles and you say, yeah, awesome, I love triangles. At this point, after thinking about this for so long, we love triangles too. But the initial motivation here was actually, again, like I said, I mean, this generalizes in various directions, and some portion of you are just going to see immediately that, how this kind of brings us forward in a certain direction. But maybe just to say something super concrete, there's a very nice networks, latent space networks model called the random intersection graph, and this non-trivially approximates the RIG. Okay, so if you care about RIG or any other kind of dependent network model, you could think of this as kind of a step in that direction. All right, now we're interested in planted models, so we're going to planted dense subgraph in the Erdos-Renyi. So we have the planted dense subgraph in our RGT, in our random graph with triangles. So we have RGT up there, that's H0, that's our pure noise distribution. And for the planted model, we're going to do exactly the same sort of planting that we did in PDS. So we take our starting graph, which is RGT, and we just planted GKQ. Now the theorem, and this is really just the whole rest of the talk is going to be focused on understanding this theorem and seeing how we achieve it and why it's true, is that for any k that's smaller than n to the quarter, P and Q are constants, P prime is no more than 1 over n log n, then there are polynomial time maps in both directions between original planted dense subgraph here and this planted RGT that we just defined. Now there's some parameter mapping here. So the planting density Q bar is not the original planted density Q, and that's just because things get denser when you add all these triangles, right? So you might expect that there's sort of a corresponding Q bar. But the point is that one can start at a particular point of this parameter space, N, K, P, Q, apply some mapping, arrive at some other point in the parameter space, and then map back and actually get essentially back to the original point. And so there's a very strong equivalence between these two problems. It's a bijection between these parameter spaces. Actually, it's not a full bijection. It's not, yeah, it's okay. So maybe the better way to think of it than a bijection is actually that there's a full equivalence class here as you trace out this P prime. Right. So starting from any particular PDS, you could put P prime as 0 here, and then one is just having originally PDS. And so one can then kind of trace out P prime, and all of these problems are sort of very strongly equivalent. Okay. Any questions about the result?
Yeah. So could you comment on the end of the 1/4?
Great. Yes. So that's sort of, we believe it to be suboptimal. You would like to get up to end of the half because that's obviously where kind of things are hard. That's what we know how to do.
So you believe it for end of the 1/2. For this.
We believe it. Yeah. Our techniques are limited at the end of the quarter for multiple different reasons. So it's going to be a serious project to improve it beyond. But we kind of believe in our hearts that it's doable. Yeah, that's one of the open questions left here. Yeah, another question, and this will become evident later, is can you improve this P prime? Yeah.
Sorry, yeah, it was about P prime. So P prime is 0. What are you saying?
Good. So if I plug in, this is saying take any P prime that's smaller than 1 over n log n. So you can put P prime as 0 here. Planted random graph with triangles with P prime as 0, you just haven't added any triangles. And so this is just PDS. When P prime is 0, the statement's tautological.
So I think the point is it's only meaningful when P is larger than whatever end of the 3/2 or something. I mean, what was
that's right.
Yeah,
that's right. It's
because otherwise you get it just based on TV distance between the two distributions.
That's exactly right. Yeah, yeah. But actually even more so. So you could start at whatever is the meaningful P prime. And what this theorem is saying is that you can vary P prime, and the complexity of the problem doesn't change at all. It's fully equivalent for this whole family of P prime. So as we think about these problems kind of parameterized by K, Q, and P prime, and we vary P prime, there's a whole family, one-dimensional parameterized family of problems that are strongly equivalent to the original problem with P prime is 0. Please, yeah. Sorry. So I should say we can't do this for Q as 1. We can do it for Q as 0.999. Yeah, and that'll become also, I think, evident in a moment why. We can say something. It's not that we can't say anything when Q is 1 for the actual clique case, but it's much weaker. Yeah. Yeah.
When you have if you translate the spectral algorithm, which works when case bigger than root n doesn't give something non-trivial for this problem.
You translate the spectral algorithm to planet RGT. I suspect it'll just work, but yeah, it should work. But I don't know how to analyze it directly. I mean, the one would have to think carefully about what happens to the spectra when you add all these triangles. But it's sort of clear it's going to work. I mean, the remark I was going to say about this P prime is that this is sort of close to the thresholds for the phase transition for a certain distribution over triangles. It's a Gibbs measure that I'll talk about. And so this is in the high temperature regime, basically, is what restricting P prime to this regime is doing. And so you might expect that various nice things are true in this regime for random graph with triangles.
The reason I'm asking is that if you look at the trivial algorithm, which is greedy algorithm that works for n above square root and log n, it's not clear it will work in this regime because the adding per pair you only adding constant perturbation that might not be visible. Maybe it is visible.
That's right.
To be verified that the algorithms work.
Certainly, the degree thresholding algorithm will certainly continue to work here. Okay. Yeah, because you're shifting everybody's degree by essentially the same amount up to a very small, up to root n. Excellent. Another question, yeah.
This dependency of on epsilon in this theorem.
Epsilon, so you're saying the accuracy that you're mapping these distributions. So this we're just taking to be little o of 1. Once it's little o of 1, then solving one problems could. Sorry?
So it's the running time of this reduction and the
I doubt it.
Is this for any
I doubt it. I think it's not true for any epsilon. This is true. The epsilon itself is a function of k. Okay, it's basically going to scale like k squared over root n is epsilon, and so that's why this end of the quarter is showing up, we need it to be smaller than, k squared to be smaller than this. Yeah, excellent. Okay. All right, so yeah, so like I said, the whole rest of the talk is going to be focused on understanding this and demonstrating that it's true. And so let's go back to our objective, which is designing a reduction. We need obviously to design reductions in both directions. Okay, so this is what we're trying to do. We're trying to map both of these distributions by a single algorithm. The algorithm obviously can't know which is the case that generated your graph P0 or P1. You just have to run the same algorithm and it maps it in both cases. Okay, so the first thing that's maybe not entirely obvious is how does one actually design these mappings? So that's step one. Step two, once this is the approach we're gonna follow, is that you're just gonna figure out how to map P0 to Q0. And then we're gonna show that the same mapping that works for P0 to Q0 continues to work for the planted distribution. So that's the approach. Here's the general theorem that follows that approach. I'm not going to dwell on this general theorem too long, but I'm just going to highlight a few things, and then we'll go about sort of working through things for this specific case of random graph with triangles. But there's something more general happening here. So just quickly parse it. So what we're going to do is we're going to think of an enumeration of the edges in the Planted Dense subgraph, but this doesn't have to form a dense subgraph. So there's E1 through E capital K. So this would be in this case k squared choose k squared over 2 k choose 2. Associated with each edge is some sampling probability. For our situation, that was Q, this elevated edge density. But in principle, you could have a separate parameter for every edge. So you could plant things that aren't dense subgraphs. You could plant things that are, very complicated, whatever you want. And then we're going to consider intermediate planted distributions. So we're going to consider, I changed from Q to P prime, sorry about that. So we're going to consider P1I plants the first I of these edges. Okay, so you start with P0 or P0 prime, and then you plant the first I of the edges. Suppose that somebody gave you or you devised some mapping that maps the pure noise distribution. Okay, so you map P0 to P0 prime. Then there's a little bit of some technical condition here. One fixes some family of graphs that have high probability under each of these models. Then if these three conditions are satisfied on your mapping, so in a second we'll parse them, okay, then the full planted distribution gets mapped with some error that scales like the number of edges that you've modified to the correct target distribution. So what are these three conditions? First condition, and this is really the important one, is that if one considers the output of your algorithm, where you take a graph G and you don't have edge E in it, and you consider it on the rest of the graph where you ignore edge E. So that's what this little tilde E is. This E, you forget about E, you run the algorithm, and you look out here, okay? And this is saying, as I change whether E is present in the input, there isn't a huge impact on, there's an epsilon impact on like the rest of the graph. Okay, so this is a sort of a sensitivity or an influence kind of a statement here. Okay, now there's various other questions. So the behavior on edge E has to be roughly independent of behavior on the rest of the graph. And finally, there's a sort of concentration statement about the actual marginal probability on a given edge that you're studying. And now back to this set of graphs G, the requirement is that for each edge here that you're planting something on, for every graph G, all these statements hold. But in our family, obviously, yeah. Okay, so this is the general theorem. If this was a little hard to parse, no worries. But the point is that there is kind of a general way of thinking about these reductions, which is
this is only for all the graphs in your family, or the set of graphs in your family, or the things that have non-trivial mass of the distribution, right?
That's right, and you get to choose it when you're applying this theorem. That's right. Yeah, so this is a new and general way of thinking about devising average case reductions for planted problems, and we're going to apply this in the setting of random graph with triangles. All right. All right, so first as kind of a warm-up, we're going to discuss a little bit the forward map. This is the direction where you add triangles. This one's much easier. Okay, so what we want is you input a PDS instance, so G, N, K, P, Q. Sorry about all the parameters. Okay, and you want to apply some mapping. We're going to call it A prime. And we're going to end up with random graph with triangles with a planted subgraph in it. Okay, so as this theorem and the kind of high level approach I talked about before, it's trying to map the pure noise first, and then we say, well, it still works when you have something planted. So the pure noise situation here with random graph with triangles is kind of obvious by the construction of random graph with triangles. We'll just add a bunch of triangles. That's what the algorithm itself should do, right? One starts with Erdos-Renyi and one wants to map to random graph with triangles, just add a bunch of triangles. And then the thing is that this actually continues to work with the Planted Dense Subgraph. And that's not terribly hard to show. It's quite tedious to show directly, but one can actually show it as part of this general theorem as well. And that's what we do in the paper. So a little bit of notation that's going to show up quite a bit is X here is distribution of our triangles. Okay, so it's Bernoulli P, product n choose 3. And A prime, we're just writing it out, takes your input graph and it takes the union with the edge set of these triangles. Okay, this mapping is very simple. And like I said, it correctly maps the planted distributions as well. Okay, yeah, so I won't get into this at all. I won't discuss it. But one can directly show this just by computing the TV. And like I said, it is somewhat tedious. It's like several pages. And yeah, but this is not the approach we take. We do apply the general theorem just as a matter of principle. Okay, so on to the other direction. This one's the interesting direction. So now we have a random graph with triangles, and we want to map to Erdos-Renyi. Of course, we want the map to continue to work in the dense subgraph planted dense subgraph case. But here, it's not even obvious how to map from random graph with triangles to Erdos-Renyi. So I'll pause for just a second so you can think about it. Okay, so one approach would be to just start removing triangles. And obviously, you have to remove triangles. There's extra triangles. So you could choose a random triangle and remove it and iterate. Who thinks that would work to map to Erdos-Renyi? Nobody thinks that would work, or people are still comatose from their heavy night of drinking. No, so right. Right. So it turns out that just completely fails. Like, that's not what you want to do. Okay, so there's something else that we do. So I'll describe that, and then we'll really focus on why should this mapping, and this is where the bulk of the technical contribution is, why should this mapping continue to hold in the planted case?
So can you give some intuition about what goes wrong with that trivial approach?
Yeah, good question.
I mean, somehow are some of the triangles that you get from the RGT like concentrated and for the density in some region, or what? Somehow it helped to understand what's the main obstacle of the technique.
Change the edge density, right? In a nice way.
I mean,
Right.
the thing is, you want to change the edge density. I mean, you're inevitably, because you're removing edges one way or another, you're going to change the edge density.
But if I do it non-uniformly,
Yeah,
it's,
correlations and
It-
negative correlation.
yeah.
How do you know that it fails? Yeah, exactly.
um,
I think it's a guess.
no, I felt pretty strongly about it. Yeah, can I prove that it fails? I mean, this realization that this fails, like I said, I mean, this is a problem I've been kind of sitting in the back of the head for, at this point, like 7-8 years. And so the moment where I convinced myself that this totally fails was like the distant past, and all those neurons have died. So that's, yeah, exactly. So yeah, it's not needed for the talk. Yeah, but maybe it's a good exercise to try to understand. But actually, now that we discussed this, it really doesn't seem that trivial to see precisely why it's going to fail. It's a good question. I mean, I think it sort of does the wrong thing with the local fluctuations of the triangle densities. So it somehow isn't. I mean, I think one has to consider a situation where it's like slightly denser here, slightly not too dense here, and then it's not correctly accounting for the kind of very local densities. But anyway, maybe it's as Yury said, it's not at all needed for this.
I mean, it would also be nice if, I mean, in the beginning, you sort of talked a little bit about the complementary aspects of like average case reduction versus low degree. It'd be kind of interesting if the reason it fails is also a low degree moment breaking.
Absolutely.
which is kind
very
of what you
likely.
expect, right?
Very likely would be.
Yeah.
Yeah. Almost certain. Yeah. All right. So we wanted to define a reverse mapping. So one way to do this that's kind of very natural once you think about it is the forward mapping added a bunch of triangles, and it's a randomized algorithm. It's really just a Markov transition kernel. And so we all know that you can time reverse such Markov kernels, and that's what we're going to do. We're just going to time reverse. So another way to think of it, if that was sort of too much jargon, the forward mapping defines a joint probability distribution on your input graph and output graph. So for a given input G prime that's Erdos-Renyi, you produce some G that's RGT. And so we're just going to consider the reverse map as looking at the posterior, as computing the posterior distribution over graphs that could have been the ones that were mapped to the one that we have, to the RGT. Very natural, right? So now we need to just describe this. Okay, so again, X is the set of triangles that are added to form the RGT. So you take the union with these edges. So if we want to expand out, condition on the X's, so we want to find the probability of Erdos-Renyi given the RGT that we have. You get condition on X. We have two factors here. Well, this one is easy to think about. If we're given this graph and we're told the set of triangles, then you erase the information on the original graph. And so the posterior is just to sample each of these edges according to Bernoulli P. So this second factor is easy. This first one is more interesting, and it's something that we're going to call mu G. Okay, so what is this mu G? Mu G is right here. It's a distribution over triangles, right? It's given the graph that we had. We're trying to find the distribution over the triangles that were added to give us the graph that we have. Okay, so here's the distribution. It has two factors here. There's the first factor that has to do with the cardinality of the number of triangles. So this is sort of a product portion of this distribution. And then there's this second one, which has this E of X, which is the number of edges formed in the union of X. Okay, so this one couples the different triangles. First remark is that the Glauber dynamics for this mixes fast in the regime that we're studying. So you can sample from this distribution, which is nice because this is a component of the algorithm. So hopefully it runs efficiently. So now the algorithm is just sample this X and then re-sample each of those edges with probability P, Bernoulli P. All right, a couple words about this distribution. Like I said, there's this sort of product part of it, and then there's a second factor which couples the edges, and this is really just kind of a soft constraint satisfaction problem. The edge is in the graph if it's like the OR of the triangles that contain it, right? So it's kind of a soft CSV, and it creates a repulsive force between the triangles. Like this has higher probability than that one because it covers more edges. Okay, so here's our theorem again, and this mapping indeed maps the null distributions, the pure noise distributions. So it takes RGT, maps to Erdos-Renyi. What we're claiming is if you plant something by resampling all the edges in a set S that's not too big, and you do the same thing in the Erdos-Renyi situation, then the theorem says that the mapping continues to work. So before we explain it, why is this surprising? Well, for one, what the theorem is saying is that, at least let's ignore the actual planted portion, let's consider the rest of the graph. So the theorem is saying that this continues to do exactly what it was doing when there was nothing planted, right? You change a bunch of the edges, but everything out here, the distribution, the way it's getting mapped is the same. And so what A does is independent of the signal. In some sense, it's kind of a weak dependence sort of statement. Okay, but at the same time, if A is removing the dependence in random graphic triangles, it necessarily has to behave in a dependent way. And so there's a tension between these two desired properties of the mapping. Okay. So the way to think of this, it turns out, or the way that we think of it, actually, this is maybe not the way to think of it because it's what gives rise to the end of the 1/4, so optimality. So yeah, maybe this is precisely the way that you do not want to think about this. Okay, so this is how we think about it and how the proof goes. We're going to enumerate the edges, and instead of resampling all of them all at once to plant the dense subgraph, we're just going to plant them one at a time. We have this notation: resample, sub edge, superscript the probability that's getting resampled. So this is obviously the same, you just sequentially sample them. And the way that this is proved to be true is considering one such resampling at a time. Okay, so the key lemma, and this is actually identical to just this condition 1 that was in the general theorem statement. The lemma is that these operations commute. Okay, so on one hand, we resample and then apply the algorithm. Here we apply the algorithm and then we resample. Okay, of course, there's an approximation error. They don't precisely commute. There's this 1/n TV loss. But once you have this, I mean, you can just think of this as you're kind of sliding over the application of A by 1. And so okay, this you don't know, but you can just slide it all the way over. And clearly, if you lose 1/n each time you're doing this commuting operation, then you can slide it over √n times. All right. Okay, so everything boils down to this kind of single small question that has to do with one edge. Okay, so in order to kind of reason about it, it turns out this is a little bit annoying, and so we're going to simplify by thinking about it for just a second. So up on the top, we first possibly add edge E, right? You're resampling with a relatively high probability. So intuitively, you first add edge E, then you apply the algorithm. Here on the blue, you first apply algorithm, which maybe doesn't have edge E. So that's why I put -E here and +E. And then you apply the algorithm, then you possibly add edge E because you're resampling with some bigger probability. Okay, so if this is what we want to show, maybe I didn't dwell enough on this. So what we're trying to show is that if you ignore edge E itself, we ignore edge E itself, we don't have to worry about like what's happening specifically on edge E here. We can just think of the rest of the graph. That's again as tilde E is. And the point is that this distribution is similar, very close, regardless of whether edge E was in the input or not. All right, so the picture, here's our graph without edge E. We have a distribution over triangles, algorithm runs and resamples things. Here we have edge E. And we're going to consider these two distributions over triangles. So instead of just having edge E in the input, we're actually going to require that the triangle distribution contains edge E. Okay, so we're now, X is the triangle distribution, right, that the A samples. X plus is it's forced to have edge E in the triangle set. Okay, but clearly, if you don't condition on here, it's the mixture of the two. Okay, so now by data processing inequality, because the algorithm is doing some operation given these x's, it suffices to prove bounds on the x's rather than the actual output of the algorithm. Okay, and then by convexity, like I said, this thing is a component in the mixture of the actual output of the algorithm here. We can instead just focus on this bottom quantity. Okay, so again, what's this bottom quantity? We are inputting a graph. We sample X according to some distribution, and we consider everything outside of edge E. So that's on the left, and we're assuming the input graph doesn't have edge E in it. So this is the picture. On the right, we just force the triangle set, or in this case, the purples, to contain this edge. And we're asking out here, are these two distributions close? Okay, is everybody on board? This is what we're going to show for the rest of the talk. Okay. All right, so maybe one remark. There's many people here who like to think about influences, and some more than others. This is different than your standard influence for various reasons, but for one, because we are changing edge E in a distribution where the basic objects are triangles. And so edge E is you're like adding a constraint essentially on your distribution. So it's not kind of a standard influence, but in any case, this is what we want to compute, this total variation between these two objects. And we're going to carry out a decomposition that's sort of analogous to chain rule for KL or these sorts of things, but a little bit different. There's something similar that can be done for total variation. Okay, so the first term in this is we consider triangles that don't contain edge E. Here in X plus, we're adding in these triangles that include edge E, but we don't want to consider those initially. So these are the sort of like these teal triangles. Okay, so first we have a TV between these kind of faraway triangles we'll think about. They're not that far, right? The ones that don't include this edge. So the question is, how much does edge E actually impact the distribution out here? And then there's a second term, which has something to do with the triangles that here are in this, I guess, red color, that do include edge E. Okay, but these are right. I think I forgot to add a okay, I mean, it's correct as stated. It's just for some reason I. Okay, no, this is completely fine. Sorry. Yeah. All right. So, okay. So the point is that there are various edges here that are a part of a triangle that contains the purple, and I mean those have an effect, right? And those were not considered up here because here we just said we're only considering triangles that are not containing the purple edge. Okay, and so basically, there's a distribution over these faraway triangles, and there's edges induced by this, and the decomposition is separately considering each. Now, one important note, though, is that in the second one, we condition on the teal triangles. These are conditional distributions. Yeah, in that sense, it's kind of like the chain rule. All right. We'll get into each of these terms, so it'll be clear. Okay, so as far as the first term goes, well, what can we do? Well, we have distance between two somewhat complicated dependent distributions. We apply the classic Inkster trick. Now, when people see Inkster trick, at least a lot of people that I know, and when I see somebody say, okay, Inkster trick, that's kind of when I immediately shift my attention to the news or something, because I mean, it's usually just some super painful calculation. It's not terribly insightful, okay? But the situation for all of those is always that there's a product distribution that you're comparing against. So there's some mixture against a product, and that's kind of how one kind of turns the crank on the Inkster trick. And neither of our distributions are product. They're both complicated dependent distributions. And so one of the innovations here is that there's a way to carry out this sort of calculation for these sorts of distributions. It's not for any distribution, obviously. And the key conceptual piece here is an inequality that relates the chi-square divergence in terms of a certain influence in the distribution. Okay, so I won't get into this, but this influence in the triangle distribution turns out that one can bound it because this P prime is sufficiently small that, you know, it's in a high temperature regime, there's decay of correlations and so forth. Okay, so this chi-square is controlled by influence, and maybe that's all I will say about this this first term. Okay, now we need to address the change in distribution. So again, we're considering the distribution on the rest of the edges except for this edge, but triangles containing this edge still have an effect because these two kind of edges are still there, right? So every time that you have such a red triangle, you observe this. This gets added to the distribution. All right, so this x plus has a bunch of extra of these as compared to the ordinary x, because I mean that initial edge just wasn't even there in x, and so that's sort of what causes their difference. But you might say, well, there's still a whole bunch of edges in x, right? So like the fact that there's a wedge getting added in the x plus, it doesn't do much because x has a bunch of such wedges that are caused by triangles that just aren't this particular triangle. Okay, and so a sketchy heuristic that might suggest that the TV induced by this is 1 over root n is just to compute the shift in mean by the standard deviation divided by the standard deviation of these sorts of wedges. And well, one is getting a constant number of these wedges. There's sort of order n such pairs of butterfly triangles that have a wedge, and so one gets 1 over root n as a very sketchy heuristic. Some of you probably aren't happy with this heuristic. It turns out that, and this is completely a dead end as far as trying to make things rigorous using the heuristic itself, but it just suggests the answer. Okay, so how does one actually make this rigorous? All right, so in the X plus distribution, like I said, we're getting extra wedges, extra 2 stars here that are just supported on this edge E that we're forcing triangles to exist on this of this red type. Okay, so the idea intuitively is, in order to compare this X plus, whereas again, we're hiding this and we're saying, what's the distribution on the rest of the stuff? To compare that with the distribution on X, we're going to try to modify X plus in a way that it kind of looks more similar to X. And so what we're going to do is, every time that there's a wedge, we're going to sort of instead add these orange triangles. We're going to explain the presence of this wedge by triangles that are legitimate in the X distribution. Okay, so we have a new triangle distribution, X tilde. It's modified from the X plus distribution. Every time this happens, you put in these orange. Now, that in itself induces some change, unless the other edges in the orange triangles were already there. And if they are already there, then you're home free. You can just, focus your attention then on what's going on these red edges. So there's a specific kind of construction, a recipe for kind of this explaining whatever these red wedges were that are in the X plus. You can convert it to this X tilde distribution where these orange triangles are added in a kind of very careful way to cover edges that were already there by other triangles. All right, now for some people that's going to be satisfying as an intuition. There's a completely kind of different way of thinking about this, and this is maybe more kind of general way of thinking about this, which is what we're actually doing. So what we have is, again, we have 2 distributions over triangles. We have a distribution over triangles that don't contain edge E, and then we have this distribution X plus where we force edge E to be in a triangle. Now, what we actually care about is the projection, so under the edge set. Okay, so there's the edge set of this triangle, of the set of triangles. There's the edge set of this other set of triangles. We wish to show that these 2 things are close. Now, the first thing, if one just blank slate, you just woke up from a very long nap, you'd say, oh, this is exactly the situation where data processing inequality applies. Let's just show that those upper distributions are close. The problem is that the TV is 1. This one on the left doesn't have triangles containing E. This one does have, so they have disjoint supports. Okay, so data processing inequality and just projecting down fails. And then what we do with this X tilde that kind of explains these triangles is we construct X tilde so that the edge set with X plus is the same. And then we show that X tilde can be shown to be close to X. And that's kind of involves part of the calculation. We compute likelihood ratio, where we add each of these triangles kind of one at a time, and then show concentration of likelihood ratio, and that shows that the TV is small. Now, by data processing inequality, this and this are close, and these are equal, and so then we've shown what we want. Okay. All right, so to wrap up, we have an interesting class of models that's equivalent. There are several new techniques in here that we hope will generalize, or we expect to generalize in various ways that we're currently working on. There's this open question of how does one extend this to k is bigger than n to the 1/4. So we have some ideas there, but like I said, there are multiple pieces in the arguments that really require this. Yeah, I'll end there. Thank you.